Hi all, this is Dr. K.G. Shanti, Professor, ECE Department, R.M.K. College of Engineering and Technology. In this video, we are going to see orthogonal coordinate systems, which is the fundamental for understanding all the concepts of electromagnetic fields. Orthogonal coordinate systems. Any physical quantity in electromagnetics is going to be a function of space and time. Right, a point in the three-dimensional space is going to be located as a function of three surfaces. That is, it is going to be an intersection of three surfaces. Right, since the three surfaces are mutually perpendicular to each other, we call it as an orthogonal coordinate system. And when I say an orthogonal coordinate system, you will have coordinates and those coordinates are also mutually perpendicular to each other. The most commonly useful orthogonal coordinate systems are, first one is Cartesian or rectangular coordinate system, second one is circular or cylindrical coordinate system, and the third one is spherical coordinate system. The first coordinate system what we are going to look into detail is Cartesian or rectangular coordinate system. A Cartesian system is one where there are three planes. Say this is the first plane, yellow color is the first plane, you have green color plane and you have blue color plane, right? So one is lying along the x-axis, one is lying along the y-axis and one is along the z-axis. I hope that everybody is clear with this. That is, you have three planes and any point P is the intersection of all the three planes. And in these three planes, what are all the unit vectors associated with these three planes? It is AX, AY and AZ. Along y direction you have AY, along x direction you have AX and along z direction you have AZ. Now look at this diagram as I told you in the earlier slide. Any point P, look at this point P. Any point P is going to be an intersection of three planes. Now how I have represented the planes? Along x direction you have one plane. See here, this plane. This plane is going to be along x direction. So you have x is equal to x1 plane. Then you have one plane. See here, this plane might be, let me use a different color. See here, this plane, that is this plane, right? This plane is the y1 plane, right? And you have one more plane, right? See here, where is that plane? This plane, that is, I'm drawing lines, right? Now this is going to be z1 plane. So you have three planes, x1 plane, y1 plane and z1 plane. So any point P is going to be intersection of three planes as represented here. See here, point P is going to be represented in brackets x1, y1, z1, right? How do I represent the position vector? What do you mean by position vector? The directed distance from origin to the point P, right? This is origin and this is the point P. And what is point P? x1, y1, z1, which means that how do you represent position vector? OP is equal to AX into x1 plus AY into y1 plus AZ into z1. X1 is the component along x direction, y1 is the value along y direction and z1 is the value along z direction. And what are the unit vectors associated with it? AX, AY and AZ. So these three are the unit vectors. And you all know unit vectors are vectors which have unit magnitude, right? Cartesian or rectangular coordinate system, any point, as I told you, you have three planes, x plane, y plane and z plane. Now let us look into what are all the three, what will be the ranges of the coordinate variables. You all know very clearly, so always for reference we use this as z and this as going to be y, correct? And this is going to be used as x, right? So, and what is the center point? The center point is going to be origin, right? Now, what is the maximum value of x? X can vary from minus infinity to infinity. This is 0. This on this side, it varies from 0 to infinity. On this side, it varies to minus infinity, correct? So, any variable x is going to vary from minus infinity to infinity. Y is going to vary from minus infinity to infinity, and z is also going to vary from minus infinity to infinity. Correct. Next is we are going to arrive at a relationship between unit vectors. Ax cross Ay. Now this is cross product. What is cross product? You all know Ax cross Ay is nothing but magnitude of Ax into magnitude of Ay into sine angle between them. Ax and Ay are perpendicular vectors. So sine 90 into the normal vector. What is the normal vector? Along the z direction, it is going to be az. So what you will have is ax cross ay is, if you want, let us write it. Ax cross ay is going to be magnitude of ax. Magnitude of ax is 1. Magnitude of ay, what is magnitude of ay? Magnitude of ay is also 1. And sine 90 degree, sine 90 degree is going to be 1. I hope you all know that. Sine 90 degree into, what is the normal vector? Normal, what is the vector normal to the plane of x and y? It is going to be z. So the normal vector is going to be z. So that is how you get ax cross ay is equal to az. In the same way, ay cross az is equal to ax, and az cross ax is going to be ay. Right? It is going to be in cyclic order, that you have to remember. Now coming on to dot product. Ax dot ay. What is Ax dot ay? Dot product. Mod of Ax into mod of ay into cosine of the angle between them. Right? Cosine of the angle, what is cos 90? Cos 90 is going to be 0. So that is why Ax dot ay is equal to ay dot az is equal to az dot ax, which is 0. Right? Now when I have a vector, a unit vector on upon itself, in that case, what you will have? Mod ax into, what is angle between the vector on itself? Cos 0. Cos 0 is going to be what? 1. Right? So that is why we have ax dot ax is equal to ay dot ay is equal to 1. Is that clear? So this is going to be dot product and this is going to be cross product. Right. Next is, how do you represent any vector in rectangular coordinate system? Any vector is going to be represented as ax into ax vector, ay into ay vector, az into az vector. Now capital Ax, ay, az, they represent the magnitude, and small ax, small ay and small az, they represent the unit vectors. Right. In the same way, if I consider one more vector, right? If I consider one more vector as b, what will be the value of b? Bx into ax plus by into ay plus bz into az. Now when I find out the dot product, what will happen? You all know ax into, in the previous slide, we have seen ax dot ax. What is ax dot ax? Ax dot ax is going to be equal to ax into cos 0, right? And what is cos 0? Cos 0 is going to be 1. So only those terms will exist and all other terms cancel. So a dot b is going to be ax into ax plus ay into bay plus az into az. Now this is going to give you the cross product of two vectors, right? And the short form we have written here, and when we expand we have to do the normal matrix expansion. Right, that is what is shown by this equation. So a cross b is going to be the expansion of this matrix. Okay, right. Now coming on to let us now analyze differential elements. Right, Cartesian coordinate system in terms of differential elements. When I say differential element, a small variation along x direction, which is represented as dx. A small variation along y direction, which is represented as dy. A small variation along z direction is dz. Right? Now how will you represent differential length? Dx into ax vector plus dy into ay vector plus dz into az vector. Right? Now this is going to be differential length. Now coming on to differential surface areas. Right? Now see here, look at this first surface. right? Now what is the side values here? Dz, and what is this value? Dy. And what is the perpendicular vector coming out from that? Ax. So what is dx x, this one? It is going to be dy into dz into ax vector. That's what is shown here. Now what is dsy? Dsy is nothing but this one. Let me mark it as 2. So it is going to be dx into dz into ay vector. There will be a vector perpendicular from the surface, that is ay here. Now look into the surface 3. When I look into surface 3, it is going to be dx into dy. And what is the normal vector? Az. And what is the differential volume? Differential volume is dx into dy into dz.